Welcome to today's session on understanding decision trees in data modeling. Decision trees, with their versatility and interpretability, play a pivotal role in the realm of data modeling. Whether you're new to the field or a seasoned professional, today's presentation promises valuable insights into how decision trees can be harnessed for predictive modeling and statistical significance testing. Here is where we unravel the intricacies of understanding decision trees in data modeling. Decision trees, in essence, are like nature's flowcharts, effortlessly guiding us through the complexities of data. What makes them stand out is their versatility and interpretability, making them a valuable asset for both newcomers and seasoned professionals in the realm of data modeling. Imagine a roadmap that not only predicts outcomes, but does so in a way that is transparent and easily decipherable. Decision trees offer just that, a roadmap that resembles a flowchart, allowing us to follow the logical path of decision-making, one node at a time. In today's session, we'll demystify these versatile models, exploring their components, applications, and the art of interpreting them. Now, let's dive into the essence of decision trees and understand why they're often hailed as the architects of predictive modeling. At its core, a decision tree is your guide through the forest of data, a sophisticated algorithm designed to make decisions and predictions. It's like the conductor orchestrating a symphony, learning from the data to create a harmonious arrangement of insights. Picture the decision tree as a tree-shaped flowchart, where each decision is a fork in the road, guiding us through the data's intricate pathways. Now let's break down the key components that make up this arboreal marvel. First and foremost, we have the root node, the pinnacle of our decision-making hierarchy. This node represents the entirety of our data set, setting the stage for the grand performance. As we descend into the branches, we encounter decision nodes, the maestros of segmentation. These intermediate nodes scrutinize specific features, deciding which path to take based on the conditions they impose. Further down, we reach the leaf nodes, our final destinations in this journey. These terminal nodes represent the conclusive outcomes or decisions, the end of the road where predictions come to fruition. And finally, tying it all together, we have the branches, the connectors linking nodes and outlining the narrative of our decision-making process. So, in essence, a decision tree is not merely an algorithm, it's a storyteller, unraveling the intricate tales hidden within your data. As we progress, we'll see how this dynamic structure plays a pivotal role in deciphering the complexities of the datasets we encounter. Now that we've grasped the conceptual framework of a decision tree, let's take a closer look at its visual representation. Imagine this as the unveiling of the branches and leaves, the graphical manifestation of our algorithmic storyteller. In the visual presented, we have a snapshot of a decision tree derived from a real-world dataset, in this case, the famous IRIS dataset. The elegance of this representation lies in its ability to convey complex decision-making in a comprehensible manner. As you gaze upon the plot, notice the intricate structure resembling a tree, with nodes branching out and leaves capturing the essence of our predictions. Each node signifies a decision point, a moment where the algorithm evaluates a specific feature to determine the next course of action. Starting from the top, we have the root node, the genesis of our decision-making journey. This node symbolizes the entire dataset, setting the stage for subsequent divisions. As we cascade down, we encounter decision nodes, the gatekeepers of segmentation. These nodes pose questions based on specific features, leading to divergent paths in our data exploration. The ultimate culmination occurs at the leaf nodes, the endpoints of our branches. Here, decisions solidify and predictions take shape. Each leaf encapsulates a unique outcome or class, contributing to the overarching narrative. The connecting lines, or branches, are the conduits linking these nodes, illustrating the logical flow of decisions from one node to the next. In essence, what you're witnessing is a visual narrative, a roadmap created by the decision tree to navigate the data landscape. This graphic representation ensures transparency and demystifies the decision-making process, allowing us to decipher the patterns and insights encapsulated within our dataset. As we proceed, we'll explore how to interpret and leverage this visual representation to glean meaningful insights from our data. The decision tree isn't just a model, it's a visual interpreter, translating the language of data into actionable intelligence. Now that we've delved into the anatomy and visual structure of decision trees, it's crucial to understand why these models hold a significant place in the realm of data science. First and foremost, decision trees are celebrated for their interpretability. Unlike some complex, opaque models that resemble black boxes, decision trees act as transparent decision makers. Imagine them as a guidebook written in the language of logic. Each decision node is a clear, concise question, and every leaf is a straightforward answer. This interpretability empowers not just data scientists, but stakeholders across various domains to comprehend and trust the decision-making process. The versatility of decision trees is another key attribute. They aren't confined to a singular role. Instead, they effortlessly adapt to the needs of both classification and regression tasks. Whether we're predicting categorical outcomes or estimating numerical values, decision trees seamlessly navigate through diverse data landscapes. This adaptability makes them a go-to choice in a plethora of real-world scenarios, showcasing their robustness and applicability. Perhaps one of the most valuable aspects of decision trees is their ability to shed light on the importance of different features within a dataset. As the tree grows and makes decisions, certain features prove to be pivotal in influencing the outcomes. This insight into feature importance is like having a spotlight on the most influential factors driving predictions. It guides us in understanding which variables play a decisive role, empowering us to focus on the most impactful aspects of our data. In summary, decision trees aren't just models. They are interpretable, adaptable, and enlightening tools in our data science arsenal. As we traverse further into the practical aspects of decision tree modeling, remember these inherent benefits. They not only make our data exploration comprehensible, but also ensure that the decisions derived are both versatile and grounded in the significance of individual features. Now that we've grasped the fundamentals and advantages of decision trees, let's explore why these models truly matter in the landscape of data science. Decision trees take center stage in both classification and regression tasks. Whether we're assigning labels to items or predicting numerical values, these models stand as versatile tools. Their inherent ability to navigate through a dataset, asking questions and making decisions at each step, makes them indispensable in solving a wide array of problems. From predicting customer churn to estimating housing prices, decision trees offer a reliable framework for various real-world scenarios. What sets decision trees apart is their transparent nature. Unlike some complex algorithms that may leave us pondering over the intricacies of their decision-making process, decision trees act as interpretable guides. As we traverse the branches and nodes, we can literally see how each decision is made. This transparency not only instills confidence in the model, but also allows us to understand the rationale behind each prediction. It's like having a clear roadmap that explains how the model arrived at a particular decision. Decision trees don't just stand alone, they serve as the foundational building blocks for more sophisticated ensemble methods. Random forests and gradient boosting, two powerful techniques in machine learning, leverage the inherent strengths of decision trees. By combining the outputs of multiple trees, these ensemble methods enhance predictive accuracy and robustness. Decision trees, therefore, play a pivotal role in laying the groundwork for more advanced and accurate modeling techniques. In essence, decision trees are not just standalone models. They form the backbone of predictive modeling, offering transparency, versatility, and a pathway to even more potent ensemble methods. As we proceed in our exploration of decision tree modeling, keep in mind the pivotal role these trees play in shaping the landscape of machine learning. They are not just tools, they are the architects of accurate predictions and informed decisions. Now that we've grasped what decision trees are and their significance, let's delve into the intricate workings of these models. Understanding how decision trees make decisions is crucial in appreciating their power and versatility. Decision trees operate with a hierarchical decision-making structure. Picture a tree, where each node represents a decision point. At the top, we have the root node, representing the entire dataset. As we progress down the branches, each decision node poses questions about the data. These questions guide the splitting of the dataset into subsets, leading us through a series of binary choices. The magic happens at each decision node, where the dataset is split based on specific criteria. Decision trees employ various splitting criteria such as Gini impurity or entropy. The goal is to determine the best way to divide the data, maximizing information gain or purity in the resulting subsets. It's like the tree asking, what feature or condition best separates the data to make more accurate predictions? As we traverse through the tree, nodes represent decision points, posing questions that guide the model's understanding of the data. These questions could be as straightforward as, is a certain feature greater than a specific value? The data continues to branch until we reach leaf nodes, each containing a final decision or prediction. It's akin to the tree making a series of binary decisions, refining its understanding at each step until it provides us with a clear prediction. In summary, decision trees follow a meticulous and hierarchical decision-making process. They ask questions, split the data, and iteratively refine their understanding of the patterns within the dataset. This structured approach not only makes decision trees interpretable, but also powerful tools for making predictions based on complex datasets. As we proceed, we'll witness how these concepts come to life in practical examples and applications. Now, let's delve into the algorithms powering decision trees. Developed by Ross Quinlan, ID3 excels in classification. It iteratively divides data based on features, prioritizing those offering the most information gain. An evolution of ID3, C4. 5 handles both classification and regression. It introduces the gain ratio as a sophisticated splitting criterion. Created by Leo Breiman, CART is versatile, tackling both classification and regression. It uses Gini impurity for classification and mean squared error for regression. These algorithms shape how decision trees are constructed and refined, each with its strengths. Let's explore the strengths and weaknesses of decision trees. Decision trees offer a clear advantage in terms of interpretability. Their intuitive nature makes them easy to understand, even for those new to the field. Additionally, they handle both numerical and categorical data seamlessly, reducing the need for extensive data pre-processing. However, like any tool, decision trees come with their set of challenges. They can be prone to overfitting, especially when dealing with smaller datasets. Sensitivity to noisy data is another consideration. Moreover, the inherent lack of smoothness might introduce instability in predictions. Understanding these aspects is crucial in leveraging decision trees effectively. While decision trees are commonly associated with machine learning, their adaptability extends to the realm of statistical hypothesis testing. Decision trees excel at pinpointing influential variables within a dataset. This feature streamlines the process of selecting relevant variables for hypothesis testing, enhancing the efficiency of your analysis. Uncovering intricate interactions between variables is another forte of decision trees. This capability allows you to identify nuanced relationships that might significantly impact your hypothesis, including nonlinear associations often overlooked by traditional statistical methods. Harnessing the predictive power of decision trees, you can generate valuable insights related to your hypothesis. This data-driven perspective enhances the depth and accuracy of your predictions, contributing to a more robust hypothesis testing framework. While decision trees offer unique insights, their application in statistical hypothesis testing necessitates a thoughtful approach. It's crucial to conduct thorough validation and comparison with traditional statistical methods to ensure the reliability and validity of your results. To illustrate, consider a scenario where we aim to test hypotheses about factors influencing decisions. Here, decision tree analysis becomes a valuable tool, helping us identify key predictors in a binary classification task based on the number of cylinders, CYL. The accompanying decision tree visualization provides a clear and intuitive representation of the decision-making process. Now let's apply decision tree modeling to a practical example using the MTCR's dataset. We'll create a binary target variable and build a decision tree to visualize the decision-making process. Before we dive into the modeling, let's ensure our data is in good shape. We'll handle missing values in the dataset to ensure accurate and reliable results. Next, let's check for outliers in our data. Identifying outliers is crucial to maintaining the quality of our dataset and enhancing the performance of our model. Having identified outliers, we'll take the necessary steps to handle them. This ensures that our decision tree model is robust and less prone to the influence of extreme values. Now let's split our data into training and testing sets. This step is essential for assessing the model's performance on unseen data, ensuring its generalizability. With our data prepared, it's time to train our decision tree model. We'll utilize the train function from the caret package to streamline the process and make it more efficient. Now, let's shift our focus to evaluating the performance of our decision tree model. After training the model, it's crucial to assess how well it generalizes to new, unseen data. In this code, we use the trained decision tree model to make predictions on the test dataset. Subsequently, we calculate the root mean square error, RMSE, as a metric to quantify the difference between predicted and actual values. A lower RMSE indicates better model performance. Conversely, a higher RMSE suggests that the model's predictions deviate more from the actual values, indicating potential areas for improvement. This evaluation step is crucial in ensuring that our decision tree model performs well in real-world scenarios. Now let's delve into interpreting the results of our decision tree model. Here, we utilize the train function from the caret package to perform 10-fold cross-validation and evaluate our decision tree model. This code employs cross-validation, a robust technique for model evaluation. The train function assesses the performance of our decision tree model using the mean and standard deviation of various metrics across the folds. The printed output provides a summary of key metrics, including RMSE, root mean square error, residual standard deviation, and R-squared values. RMS. This metric measures the average magnitude of the residuals between predicted and actual values. A lower RMSE indicates better predictive performance. Residual standard deviation. This represents the standard deviation of the residuals, providing insights into the spread of prediction errors. R-squared. The proportion of the variance in the dependent variable that is predictable from the independent variables. A higher R-squared value indicates a better fit of the model to the data. These results offer valuable insights into the overall performance of our decision tree model, aiding us in making informed decisions about its suitability for our data set. Moving on to the next step in interpreting our decision tree model results, let's take a closer look at the resampling results. We extract and summarize the resampling results obtained from the cross-validation process. These results include performance metrics such as accuracy, kappa, and root mean square error, RMSE, for each fold. This comprehensive summary aids in assessing the model's consistency across different subsets of the data. Accuracy. This metric measures the overall correctness of the model's predictions. Higher accuracy values indicate better overall performance. Kappa. The kappa statistic measures the agreement between predicted and actual values, correcting for the possibility of random chance. Higher kappa values suggest better than random agreement. RMSE, root mean square error. Similar to the explanation in the previous code snippet, a lower RMSE indicates better predictive performance. By scrutinizing these resampling results, we gain valuable insights into the stability and reliability of our decision tree model, helping us make informed decisions about its overall performance and suitability for our predictive modeling task. Now, let's delve into the final stage of interpreting our decision tree model results, focusing on the importance of different features in our model. We extract the decision tree model from our training object and identify the importance of each feature in making predictions. The variable importance output provides a numerical score for each feature, indicating its importance in the decision-making process. Higher importance scores suggest that a feature has a more substantial impact on the model's predictions. By inspecting these scores, we can identify the most influential variables and prioritize them in our analysis or further modeling efforts. This information is crucial for understanding which variables play a significant role in the decision-making process of our model. By printing or visualizing the feature importance, we obtain a clear picture of the hierarchy of variables, allowing us to focus on the most influential ones. This insight aids in refining our model, optimizing its performance, and gaining a deeper understanding of the factors driving its predictions. In this section, we employ the rpart.plot library to create a graphical representation of our decision tree model. Visualization is a powerful tool for understanding the structure and decisions within the tree. The visual output provides a clear and intuitive overview of how the model partitions the data based on different features. Each node, decision, and branch is visually represented, making it easier to communicate the decision-making process to stakeholders or collaborators. Additionally, color-coded elements, such as the box palette =, blues, can enhance the visual appeal and help emphasize key aspects of the tree. Utilizing visualization tools not only aids in model interpretation, but also facilitates effective communication of complex structures, making decision trees more accessible to a broader audience. In wrapping up our discussion today, we've delved into the fundamental concepts of decision trees and highlighted their paramount significance in the realm of machine learning. Decision trees stand out for their interpretability, offering a clear understanding of the decision-making process. They prove to be versatile, adapting seamlessly to both classification and regression tasks. We've harnessed the power of the RPart package and the streamlined modeling capabilities of the Caret package. This efficient combination facilitates a unified interface, simplifying the training and evaluation of decision tree models. Visualizing decision trees plays a pivotal role in enhancing our understanding and interpretation. The graphical representation helps unravel the intricate structure of the tree, making it more accessible and comprehensible. We've touched upon the unique application of decision trees in statistical hypothesis testing. By aiding in variable selection, exploring interactions, and providing predictive insights, decision trees bring a valuable data-driven perspective to hypothesis testing. In essence, our journey through decision trees has equipped us with not only the technical knowledge to leverage these models effectively, but also the practical insights to navigate the complexities of real-world data. As you embark on your data modeling endeavors, keep these takeaways in mind, and may your exploration of decision trees be both insightful and rewarding. Thank you for your attention.